Hello, everyone, and welcome. My name is Liz Pimper, and I'll be your moderator for today's WJE webinar, Vintage Building Renovations, How to Avoid Costly Pitfalls Due to Dirty Steel. During the next hour, WJE engineers Christine Freisinger, Conrad Paulson, and Robert Warke will provide a history of vintage steel and the steel-making processes that lead to dirty steel, explain the use of metallography for detecting soundness concerns, and provide guidance for designing joint details. This presentation is copyrighted by Wis Janney Elsner Associates. And now I will turn it over to Conrad to get us started. Conrad?
Yes, thank you, Liz. I would like to welcome everybody here today. I am Conrad Paulson, a principal in the WJE Los Angeles office. However, before that, I spent many, many years in the downtown Chicago office where I learned to work with vintage buildings that were built anywhere from the 1880s through the 1930s. And they're a very great class of buildings to work with. And we're going to talk today about one particular feature, dirty steel. There will be three of us presenting to you today, and in a minute, I'll explain how we're going to divvy up the talk to us. What you have here is our learning objectives. The focus, again, is working with vintage steel in these older buildings. We're going to do our best to avoid serious technical jargon, but inevitably, we're going to talk in some technical language, and we'll do our best to present that to you in an understandable manner. Our outline today is going to start with the first half of a case study that'll be presented by Chris, and then Robert will start talking about a topic called soundness of the structural steel, where Robert will take you almost literally inside the steel. I'll talk to part three about welding considerations. That will get us a little bit into engineering speak, but again, we're presenting this in a manner that everyone on the call, whether owner or manager or architect or constructor, you'll understand what's going on. And then part four, Chris will wrap up with the conclusion to the case study. So why are we here today? With the vintage steel in these older buildings, the steel is nicknamed, quote unquote, dirty steel. And that's not surface dirt that you would clean off with some spray and a brush, but instead it is actually problems within the thickness of the steel, unsoundness defects in the metal matrix itself of the steel. The reason why this is boiling up now is most engineers with modern education don't encounter dirty steels in either new design or in their education. And that's because steel quality manufacturing is significantly better today than it was in the 1920s, 1910s, so on. Today's engineers, you can just do what we will call a compositional analysis to tell you about the weldability of the steel. Robert will delve into more detail on that, which is necessary indeed, but that doesn't tell you the whole picture when it comes to these vintage steels that might be dirty. Some of the technical information we talk about today is coming out of AISC task group, American Institute of Steel Construction is what the acronym means. There's a group of three of us who are working on the topic matter of welding to old steel. So over the course of today, we're going to introduce you to a vintage steel building. We'll explain what we mean by soundness of the steel, and in contrast, what is an unsound feature. We'll talk about weldability. And if you have an unsound piece of steel, there's a chance that you'll develop lamellar tearing in the steel in the vicinity of the weld, and we'll get into that. Again, we'll touch a little bit on engineers' topics of what to think about when you specify welding to these old buildings. And then we'll, via the case study, talk about how to sample and plan a testing program. And with that, we'll go off to Chris Freisinger to start out the case study. Chris, take it away.
Thanks, Conrad. And thanks to the audience today for joining us. I work in the Chicago office of WJE and am fortunate enough to work in many of these vintage steel buildings that we have downtown. Today, I'll share a case study with you to outline the steps that we took on a recent project. So what do we mean by a vintage steel building? We're using this term to refer to buildings that were constructed with steel before steel was fully standardized. Standard specifications for easily weldable steel structures were not written until after the mid to late 1950s. Consequently, steel frame buildings constructed before 1960 may exhibit some features that adversely affect welding. And as Conrad noted, these steels are sometimes referred to as dirty steels. Robert will talk a little bit more about this in the next section. Property owners and managers of vintage buildings, as well as designers developing renovation projects and contractors performing the work, should be aware of the potential structural concerns for dirty steel as planning for a renovation project is starting. So at the start of the project, there's a few tasks we can take to assess the potential for dirty steel concerns. We can review the original drawings for specified steel standards. We can also review the original design connections to see what type of connections were used, riveted, bolted, or welded connections. And we can also talk with the building management team to determine if metal soundness had been previously reviewed. To illustrate the structural concerns of dirty steel in a renovation project, we're using a tenant renovation project that we worked on recently in Chicago. This building was constructed in several phases in the 1900s and the 1910s. To give you a sense of where we're going, here's one of the early renderings from the design team. The tenant was expanding and wanted to lease the 4th floor in addition to the 5th floor. And to increase collaboration between the floors, there was interest in constructing a monumental stair to connect the floors together. Here's a look at the 4th floor when we first arrived on site. And you can see at the exposed columns, we do have some riveted connections, which is one of our first keys to understanding the original design. You can see the orange painted steel that's below the drywall at the columns in the photos. Typical structural framing at this building, which is consistent with the vintage of the building, consists of structural steel beams that support flat clay tile arch floors. The columns, as we noted before, are built-up steel sections that consist of angles and plates riveted together. And again, note that, we don't see any welds in these details, which is a hint that, the steel was manufactured before specifications were written to really help with welding. Anyone who works in existing buildings knows the first rule, which is to find out if the existing drawings are available. So we worked with the building engineers and the building owner to review their paper files and electronic files to organize the existing drawings into a complete package to dig into the history of the building. It turns out that this building was constructed in 8 phases, which is also not unique to this era. And some of the phases required existing portions of the building to be removed and replaced. The plan of the 5th floor notes, this plan is noting the different construction dates for each section of the building, and our stairs within section 1, which was constructed in 1905. I will say that we jumped for joy when we realized we had our floor plans, and then I cried a little on the inside when I realized the poor quality of the scan right in the area where our stair was going to be going. We had received this electronic file from the building, and someone had previously renamed the electronic file "Not a Good Scan." This is often the case for vintage steel buildings. The drawings have been around for a while and sometimes been copied and copied, and you often may find portions of the drawings that are illegible. So in our office, we often use the phrase "reading tea leaves" to describe scans like this. If you stare at them long enough, you think you can kind of squint and read them. So we ended up moving forward with an investigation phase to help us confirm member sizes and connections within the vicinity of the proposed stair. The design for the monumental stair itself wasn't too complicated. We needed to install girders between the columns and then run the stringers, keeping in mind that we needed to put into place detailing for the stairs, the bleachers, and the guardrails. Here's an overview during construction with the 5th floor framing removed, and you can see the spaces feels much bigger and more light. Here's another construction photo with the girders and the stringers and the stair treads installed. We used HSS sections to help provide stability and limit deflections for the stair. This is a photo that shows we're getting closer to the final stair being installed. You can see now that the bleacher framing in between the treads has been installed. So back to the design. How can we assess the existing steel to make all of these connections of the girders to the columns? For anybody that specializes in renovations of historic buildings, you may be thinking, these built-up columns look really cool, right? That's what I thought as well. But we have to keep in mind that one does not simply treat old steel like new steel. Design teams should keep in mind, for buildings constructed in the early 1900s, the ASTM standards were starting to take place. And for buildings constructed before 1950, bolts and rivets were the primary means of making connections. This means that the historic steel we were working with for this project might not be weldable or might not have a base metal soundness that we would like to see for welding. So now we'll head off to Robert and Conrad to give some more background and information on dirty steels, and then we'll come back to our case study to see how we finished assessing the steel.
Thank you, Chris. I'm Robert Warke. I'm a metallurgist in the Metallurgy and Applied Mechanics group at WJE. And I'm going to talk to you about base metal considerations in historical steels with particular emphasis on the soundness issues. The word weldability it's often used as a binary term, but it's really more of a relative term. With very few exceptions, any metal is in some form or fashion weldable, but it becomes prohibitive if the cost of doing so, the precautions necessary, exceed the benefits. The definition that AWS gives is the relative ease with which a material may be welded to meet an applicable standard. For structural steels, weldability is semi-quantitative, and it focuses on carbon equivalent, which is a way of assessing the tendency of the steel to be susceptible to something called hydrogen cracking. The photograph on the right is a section through a steel that has experienced hydrogen cracking. And this carbon equivalent value is based on what I call the bulk composition of the steel. That's the average composition. It doesn't account for any of the sort of segregation of elements or the concentration of impurities in any one place. And weldability is also affected by the thickness of the base metal because that affects the cooling rate of the weld, also the amount of external restraint that's applied. So the stiffness of the structure into which the welded member is being connected also affects the way that the weld is going to behave. Steel with poor weldability may require special precautions, especially preheating. However, this is rarely an issue with historical structural steels. The most common by far is ASTM A7. The compositions of ASTM A7 are extremely weldable. They're almost never an issue with this. There is an exception to this. There's a steel designated A94 that occasionally comes up. It didn't come into being until 1962 as an ASTM standard. This particular steel, if you have it, it does not follow the same rules as A7 by any means. It requires special precautions. It has significantly higher carbon and alloy content than A7, and should not be welded without applying those precautions. So weldability matters in general, but assessing it in terms of carbon equivalent and hydrogen cracking it's necessary, but it's not sufficient. And it's rarely an issue for historical steels from the hydrogen cracking standpoint. We also need to assess the internal soundness of the existing base metal. And the answer to the why question is today's main topic. So what is internal soundness? The common definition is free from defect or dependably solid. Soundness concerns arise when the base metal is unsound, that is, it contains unacceptable internal flaws. Analysis of bulk composition is an unreliable predictor of soundness. As I mentioned earlier, we will typically do an analysis of composition to identify the overall weldability of the steel. But it doesn't really tell us if there are localized issues. And the primary issues that occur with soundness in historical steels are localized and often are undetected by bulk composition. So these things are typically assessed by microscopy, which is specifically, in our case, metallographic examination. So we take a section, we polish it, if necessary, we etch it, and examine the microstructure. And this assessment should be done by a qualified metallurgist who has experience with welded joint design and with the special sort of quirks and foibles of historical and obsolete steels. What does unsoundness look like? Well, this photograph on the right is a longitudinal section through a steel that was manufactured in about 1905, and it contains, in this view, it contains a lamination. A lamination is a high concentration of impurities that gets rolled into the structural member in the steel mill. It doesn't always appear quite as distinctly as that. Sometimes it's just clustered or numerous stringer inclusions, stringer being the way they appear in these longitudinal sections. They appear like strings. Sometimes there are voids. Generally speaking, inclusions and laminations are the things that we're looking for in these historical steels. What is rolling direction? I meant to point out on this previous slide, you see down there at the lower left of that photograph, rolling direction. That's important because the inclusions in the steel are rolled out. They're rolled in the direction, they roll in the direction, or they get extended in the direction of rolling. So the rolling direction is fairly obvious from this photograph what that refers to. It's from left to right in the right-hand view. So lamellar tearing is the thing that we want to avoid. That's the problem that we sometimes encounter with these historical steels. And it's caused by these inclusions or laminations. And as I said a minute ago, inclusions in steel are rolled long and flat. If they're too large or too clustered, the steel may lose too much of its through thickness ductility, which you can think of as stretchability. When this happens, the steel becomes unable to handle the ordinary shrinkage strains from the weld when it solidifies and cools and imposes its thermal strains on the steel. This can result in internal ruptures, very microscopic ruptures between the inclusions and the steel around them. And then when a load is applied, these planar ruptures get joined together, and they end up looking sort of like what wood looks like if you split it lengthwise along its grain. And that's the characteristic appearance of lamellar tearing. In something called a scanning electron microscope, if you examine the fracture surface, the fracture phase of lamellar tearing versus other kinds of fracture, there are distinct differences. On the left-hand side is a piece of steel that was rather dirty. You can tell by all those sort of, they look like holes in the surface. Those are places where inclusions were sitting. But this steel fractured after a large amount of strain because the strain was imposed parallel to the inclusions. In lamellar tearing, the strain from welding is imposed perpendicular to the inclusions, and that's what causes these ruptures to occur inside the steel. Unsoundness in steels has a tendency to be age dependent. From left to right on the screen, you see a steel from 1922, 1905, and 1896. The rule of thumb is the older it is, the more likely it is to contain laminations and large inclusions. However, that's not always the case. On the left is a steel from 1903 that exhibited quite a bit of cleanliness, and a steel from 1960 that obviously did not. So there's no absolute rule when it comes to the age of steel. All of these sorts of problems tend to be intermittent, even in the age when before modern steel making. Sometimes steel was very clean, and sometimes it wasn't. There just wasn't that much consistency. The reason why historical steels are more prone to this, and this is a much more complex and lengthy story than we have time to talk about here, but I'll just put it in the smallest capsule that I can, and that is in those days when they would cast an ingot, and the way that this works is they would cast the ingot and then later reheat the ingot to roll it into a structural shape. So when they would cast the ingot, when it would solidify in the mold, it would solidify, of course, from the outside in. So all of the segregation of impurities would wind up in the center, along the center line of the ingot, and toward the top, because that's the progress of the solidification that occurred. And they would have to chop off a percentage of the top of the ingot before they started rolling it into a structural shape. And if they didn't chop off enough of it, or if there was an abnormal quantity of impurities down the center line, those impurities would end up being rolled into the steel, and they would get longer and flatter as the structural shape got rolled. At the lower right is a photograph of two cores that were taken out, and this is how we typically evaluate historical steels. We have cores taken out, and we do our analysis of the composition and the microstructure, that is, with our metallographic examination, to look for the unsound characteristics. The core on the left actually delaminated while it was being cored, so it had a rather large lamination in it, and that steel would be susceptible to lamellar tearing if it were welded. What steels are sound steels? The benchmark for what we call modern steels would be those steels that are made with welding in mind. And that began to happen in the mid to late 1940s. In the 50s, we started having standard specifications, and it went from there. But prior to World War II, it was far less common for steels to be welded. They were usually riveted. And so the steel mills weren't particularly concerned about the weldability or the tendency for lamellar tearing in those days, because they didn't expect it to ever be welded. Except that now, when you're trying to add steel to a historical structure, you need to know. So steels that are listed in AWSD 1.1, which is a structural steel it's a structural welding specification for steels. Those steels are considered sound and weldable. ASTM A441 and the now obsolete A373. If you come across those, you are probably in luck, and you shouldn't have too much trouble. I'm not going to tell you not to evaluate them for weldability or internal soundness, but you're likely to get away with it if you don't. Let's just put it that way. Occasionally, modern steels are unsound, just a lot less often than historical steels. So what about historical wrought iron? This is not a steel. This is a predecessor of steel. It's essentially nearly pure iron, but with large silicate inclusions throughout it. And these are large enough to be a serious issue for lamellar tearing. So if you need to attach something to a structural member that's made of wrought iron, I would advise you to find a way to do so without welding. Much the same for cast iron. Cast iron is even more problematic than wrought iron. It can contain cold shuts, which are places where solidification did not complete itself, and you have sort of a large flat area that's not fused. There can be entrapped air and foundry sand. So in this case, this is a cross-section through a cylindrical column where the core was offset inadvertently and caused one side to be thicker than the other. Above and beyond all of that, the internal microstructure of cast iron consists of steel, essentially steel, embedded with millions of graphite flakes, and these graphite flakes are a serious problem for welding. It's very difficult to weld cast iron without cracking it. What are some possible remedies for lamellar tearing? First of all, one way to do it is to create a strain buffer by depositing a pad of weld metal onto the existing steel where the connection will be, and then you weld your new steel to the pad. That helps to distribute the strains. Excuse me, I just forwarded. That helps to distribute the strains, and they're not as concentrated and are less likely to be a problem for the internal occlusions. Reduce all available hydrogen, which basically comes down to keeping everything clean and dry. That includes your welding electrodes, all of the surfaces. As the cleaner and drier everything is, the less likely you are to have problems with hydrogen. Preheating can help to remedy lamellar tearing, but I think the best and most reliable way is to change the joint design and/or the location of the joint. So I'm going to talk about weld joint considerations in regard to lamellar tearing. So if the steel is susceptible, and this is the rule that you need to follow if you want to avoid lamellar tearing, minimize the concentration of through thickness strains on the steel that's susceptible. So I won't go through each and every one of these little diagrams, but the idea is design the joint and weld it in such a way that you don't concentrate through thickness strains in the structural member that you know to be susceptible to lamellar tearing. Lastly, weld orientation. The unsound regions, as I've been saying, are elongated in the direction of rolling. So they're kind of long and skinny, like inside the steel. So if you attach something to the structural member that has that susceptibility, you're better off making your welds perpendicular to the rolling direction than parallel. Parallel welds are more likely to cause lamellar tearing, because if one of these areas, these susceptible areas, happens to be directly underneath that weld, it's very likely to tear it out. Whereas if you weld across, it spreads out the strains more, it doesn't concentrate them in that area, so you're less likely to have a problem. So that's all I have to share for the time being, and I'll turn it over to Conrad now.
Thank you, Robert. Over the course of Robert's discussion about soundness of steel and how it relates to welding, he mentioned a document called AWS D1.1, and that's the standard for structural welding. It's published by the American Welding Society. D1.1, it is a document that is under frequent maintenance and update by the American Welding Society, and it is directed primarily towards new construction. In other words, this document anticipates that you'll be using newly manufactured steel. The linchpin, at least for today's presentation, that AWS D1.1 guides us through is something called the WPS, the Weld Procedure Specification. To develop a WPS, AWS D1.1 has a means of developing what's called a pre-qualified WPS, and that is essentially D1.1 contains essentially a cookbook for the recipes you need for making a pre-qualified WPS without having to do any testing. Whereas if you can't use a pre-qualified WPS, there's a separate section of D1.1 devoted to how do you qualify a WPS, and we'll touch on that ever so briefly in a slide or two. So what goes into one of these weld procedure specifications? A WPS is shown graphically on the right portion of this image, and there are many variables that go into this WPS, probably 40 or 50 total. If you look at all the cells that are filled in this tabular format of this WPS, you'll get an idea of what's going on. And this WPS is used by the tradesperson in the field, the welder who is making the weld, and it tells the welding person what settings to use on his machine, what process to use, how many passes to put in the weld. The graphic illustration on the right there is a cross-section through the weld, and this weld is a multi-pass weld shown here of maybe a dozen passes of the electrode building up the beads of weld with each pass. But there are the major things that need to be considered here are what type of welding process, what is the base steel, and what are the permitted electrodes. The base steel is, in our case, this vintage historical steel that we were talking about. As I mentioned, this document is oriented towards modern steels, and therefore there is a section in AWSD 1.1 that has a list of the ASTM manufacturing specifications that it considers appropriate to use with pre-qualified welds. The steels and their ASTM standards that are mentioned in this list are presumed for two things. They are presumed to have been manufactured to be weldable, and they're also presumed to have been manufactured using quality control procedures so that new steel has good soundness. And it is this focus of AWSD 1.1 that it is primarily working with new steels that are presumed to be sound, that we need to set aside that concept when we are dealing with vintage steel. And if you are dealing with the vintage steel, and if you do know the ASTM manufacturing standard, it will most likely not be on the list, and that is nicknamed an unlisted steel. Essentially, AWS D1.1 is like the bouncer of welding. If you are not on this list, you cannot use a pre-qualified WPS with that piece of structural steel. However, you can use qualification procedures to develop a WPS by other methods. And that typically involves some sampling and testing of the steel. And the testing Robert talked about in his section of this presentation satisfies 95% of the need for qualification testing of a WPS. On rare occasion, you'll want to take the added step of taking a piece of your historical vintage steel and making a sample weld to it and testing and examining that sample weld in the laboratory, but that procedure is infrequently necessary. Only on certain occasions would you go to that step. Otherwise, the soundness evaluation by microscopy and the compositional analysis for the chemicals that are in the steel, that typically gives you enough information to develop your WPS by qualification. So for the engineer, how about some considerations for making new welds to older steel? And what we're going to see on the next few slides has been informed by the welding to old steel group that is formed within the AIST subcommittee that I chair. As Robert mentioned, there's a couple of older steels, ASTM A373 and ASTM A441, that are manufactured from the get-go with an intent to be weldable. And so those you don't have to worry about. Also, certain narrow spectrum of ASTM A7 steel, and A7 is an unlisted specification. It's been around since 1901 and was finally withdrawn or became obsolete in the middle of the 1960s, and so it had a long run. However, the quality control at the steel mills during that era just wasn't up to what we have today, and so there are times when you need to be concerned about welding to this older A7 steel. However, there's a narrow window of opportunity, shall we say, if you have a piece of A7 that was manufactured after 1960 and where the maximum thickness of that piece of steel is 1.5 inches, then most likely you have both a weldable and sound steel, and it would be okay to use a WPS with that. If you take this approach, however, one caveat is your steel needs to be conclusively identified as one of these standards in the available original construction documents. You'll want to assess soundness by microscopy, as Robert alluded to, based on the age of the steel. For a building constructed, before 1930, yes, almost certainly you need to use microscopy to look for these concerns of unsoundness in the steel. For steels between 1930 and roughly 1960, you should strongly consider it. And in fact, that year 1960, we'll probably need to move that up to 1970, given the example Robert had, again, reproduced on the left here. That's a piece of ASTM A7 steel from the 1960s, and that has serious soundness concerns. Now, what about a case where you have either outright unweldable steel or severely unsound steel? Then consider bolted connections. Remember, historically, bolts and rivets were the practice anyway. Conventional high-strength bolts will work. There are proprietary quote-unquote blind bolts, essentially one-sided bolt. You can install those from the accessible side of the structural steel connection, and you can also drill and tap holes and insert a threaded bolt from a one-sided situation. And with that engineering overview, we'll go back to Chris to finish up our case study.
Thanks, Conrad. So now that we've learned a lot about dirty steels and how we can assess them in the laboratory, let's go back to our vintage steel building. And we stopped at the part where we were discussing that one does not simply treat old steel like new steel. So let's take a look at how we moved forward on our project. So on our drawings, we didn't have any ASTM specifications noted. So without knowing the ASTM standard, we now determined that we need to do a little bit of digging around to determine the yield strength and the weldability of the steel. Remember that we only need to determine the weldability if we do want to use welded connections. And in this case, we did. These days, contractors do like field welding. It's a little bit easier than bolting, so it's often requested. As we mentioned before, our section of the building was constructed in 1905. So first we headed over to the AISC Design Guide 15 to see what steel was standard during our construction. Keep in mind that steel mills were producing steel and the ASTM standards were just starting out at this time. So not all steel mills were making exactly what the ASTM standard was specifying at that time. You can see that the yield values for our steel, which are the years are highlighted in green, could end up being 35 KSI or 30 KSI or 28 KSI between 1900 and 1913. We were not able to take samples of our steel until construction started. So for the fifth floor analysis, we ended up assuming in our initial analysis that we had 28 KSI yield strength steel, knowing that that would hopefully be on the conservative side. To evaluate the yield strength of our steel, we asked the contractor to remove 5 coupons. The coupons were sized to be 4 inches by 10 inches, and those coupons were used for yield testing. We ended up taking samples from a variety of beam shapes. Keep in mind that steel in the mills is produced in heats, so you want to test a variety of steel shapes on site to get a range of yield testing results for the steel that you could have. We then ran a statistical analysis based on Conrad's 2013 APT article to set the lower bound values for us to use in our design. So the statistical analysis led us to use 27 KSI, and with the values that we were testing at, we probably could have gotten a higher yield value if we had taken more coupons. For the metallurgy review, we removed 5 coupons again, and we used 1-inch diameter steel cores. And these cores were sent to Robert at the Janney Technical Center of WJE for review. We took the samples here, again, from a variety of shapes and made sure to mark the direction of rolling on the cores so that Robert would have an easier time in the lab determining where to look for inclusions. So Robert gave us a call and said we had the inclusions. And we've talked about these before on several other slides. You can see the inclusions specifically in the steel from our building. And based on these results, we concluded that our steel does have enough inclusions that we should reconsider our welded details. It turns out we had inclusions in all 5 of the cores that we obtained from a variety of different sizes. So we reviewed our welded connections again. And for our case study, here we're going to take a look at 2 connections specifically, the upper girder connection to the columns and the lower girder connection to the columns, to review the original welded details and then show you how we modified those details. So at the upper girder, we originally designed a seat that was welded to the existing column steel. And that connection design induces a concentrated tension load in the top of the seat. This tension load we now want to avoid due to the knowledge of having inclusions in the steel. There could be a chance that when that tension load is applied, it could be applied to steel that has an inclusion in it. So we revised this connection to be a seat that was attached to our column reinforcement. We ended up reinforcing the columns due to longer unbraced length since we removed a portion of the 5th floor. So the new revised connection now induces shear forces into the existing steel, and the shear forces reduce the potential for lamellar tearing. At the lower girder connection, we originally designed a seat attached to the existing column steel flange. The connection here also induces a concentrated load at the top of the seat. This tension load we also want to avoid due to the knowledge of the inclusions in the steel. Due to the occupied space below the 4th floor, we were originally trying to avoid any demolition in the 4th floor framing. But based on our knowledge now, we decided to ask the contractor to perform an inspection opening so that we could document the girder and the connection below. We ended up being able to design a seat to sit onto the connection below once we had the geometry of it. And now this load removes all tension from the existing steel. Here's a final view of the stair. The design team and the tenant were very pleased with the final look, and all of our fancy connections ended up being covered up. Back to Conrad.
All righty. Thank you, Chris. Here at the end, we're having a pop quiz, and we'd like to ask you to make your selection from the radio buttons here on the left of this screen, A through E. Which of the following ferrous structural metals are not good candidates? Again, not good candidates for structural welds. Historical cast iron and historical wrought iron, obsolete steels from before 1930, specifically A7 and A9, silicon structural steel, ASTM A94, or choice D, meaning both A and B, or choice E, all of the above. We'll give folks a few more seconds. All right, so we have more than half of the folks responding, and here is how it went. And this was indeed a tough one. The answer we were looking for actually is all of the above, although the runner-up A and B makes sense also. Based on what Robert taught us about the ASTM A94, the silicon steel, you can technically weld to it, but it is really, really difficult to get an economical weld. And so if you take that perspective, that one is not a good candidate, although it is theoretically possible. And the message here is for all of these steels, if you want to weld to them, you need to take a due cautious approach to making those welds. And as Robert mentioned, for category A, historical cast iron and historical wrought iron, you want to avoid welding completely to those. With the cast metals, just a caveat, there are modern cast metals that are weldable. Here we're talking about the historical cast iron, like the column Robert showed you, and in that situation, this historical gray cast iron, our advice is do not even consider welding. So how do we avoid the costly pitfalls we mentioned in the title of this presentation? Our recommendation is investigate early in the design process. Preferably, even if you can do this investigation of your vintage steel before you start the design process, that's even better. Again, as we've discussed, use metallography, perform a compositional analysis, do the tensile testing that Chris Freisinger illustrated. That will inform you on the concept of, can you weld or do you need to use a bolted connection? You may end up with an old steel that cannot be economically welded. You'll have to use perhaps very expensive electrodes, preheat, interpass temperatures, other procedures in the field that add to the cost of making a weld. And so it's not just an unweldable steel you need to be cautious of, but a situation where to properly perform the welding to the vintage steel, it gets economically unfeasible. In that case, whether it's unweldable steel, unsound steel, or economically not possible, you'll want to use bolts or some other type of mechanically fastened connection like we mentioned. And if you identify this early in the process, that will be fine. You'll put out a set of construction documents that say use a bolted connection. If you discover this too far down the design process, or even sometimes people don't discover this until the building is under construction and the weld cracks or the base metal itself fractures off, then you end up switching to bolted bolted connections during construction. And as you can imagine, that is a potentially costly change. And again, our main message for today, these older vintage steels were not manufactured with the same quality control as today's modern steel. And you have to use microscopy to go looking for these unsound features. If you don't do that, you stand a chance to suffer lamellar tearing in the welded connection that you might make to a piece of unsound vintage steel. The thing to remember about this, lamellar tearing, yes, it's a low probability occurrence, but it has rather high consequences if you have one of these welded joints fail and the structural member comes crashing to the floor. And so you want to avoid that kind of situation. And with that, we'll open it up to questions and answers.
All right, thank you, Conrad. As a reminder, you can type your questions into the Q&A box and hit submit, and we're going to try to get to all the questions in the time we have remaining, but if we aren't able to get to your question, one of the presenters will follow up with you afterward. Okay, let's take our first question. Is hydrogen cracking the same as hydrogen embrittlement?
I'll take that one. This is Robert. They are the same, essentially the same cracking mechanism. It's just occurring in different contexts. Hydrogen embrittlement is usually associated with hydrogen introduced by a process like electroplating, whereas hydrogen cracking is usually associated with welding. So it's essentially the same mechanism. Different steels typically, and different situations, but the underlying metallurgical phenomenon is the same.
Okay, our next question, this is for Christine. Regarding reinforcing of the column at the stair, how is reinforcing connected to the old steel?
Yeah, so we didn't touch base on that very much in the presentation, so thank you for the question. We ended up welding on we ended up using bent plates, bent into the shape of angles. With the bent plates, we could avoid the rivets, and we ended up stitch welding those pretty frequently. So with the stitch welds, we're able to gain some confidence that if some of the stitch welds end up being at locations of inclusions, we have adjacent welds that are likely not at locations of inclusions. So we're increasing the amount of times we're attaching to the existing steel to lower the risk that we will be at a location of an inclusion.
Okay, the next question. Can you give us some advice on how many coupons to test?
That probably several of us will answer that. It depends on the downstream purpose of the coupons. Are you doing metallography or compositional analysis alone? And we'll turn that back to Robert in a moment for that. The other purpose for taking coupons is for tensile test properties. And to develop particularly if you're going into a building, you have no idea about the ASTM standard used to manufacture the steel, and you want to assess the yield strength of this unknown steel, you need to think about statistical distribution, and you want to find a lower bound to the strength of the steel. You don't want to find the mean value. The AISC structural engineering design provisions actually use the lower bound of the yield strength for design. And to do that, you probably need a sample size of anywhere from 5 to 8 coupons. You want to sample different members to intentionally mix up your sample so that you don't sample from, repetitively from the same heat of steel. So only once from the W12, only once from the W14 member, and so on. And then you would do a statistical analysis called a one-sided tolerance limit, such that it is 90% confident that 95% of the yield strength test data fall above that lower limit, and you'll end up with what's called the equivalent to a specified minimum yield strength. Now, for the purposes of soundness assessment and compositional analysis, I'll ask Robert to speak up on that one. That's his area of expertise.
The chemistry, the intended chemistry of the steel as created by the steel mill doesn't vary much at all from point to point. What does vary is, again, the internal soundness. And I would say if you have a structural member, if you can take at least 2 cores out of it from 2 locations that are as distant from each other as you can get them, I think that suffices as a bare minimum. If you can take more than that without compromising the structure, probably up to 6, I would say.
Okay, our next question. Do imported steels conform to ASTM standards?
Generally speaking, they do. Many countries have their own steel standards. And if you compare their requirements to ASTM's requirements, they're typically at least as stringent, and the quality of steel coming from that country is in conformance to their standards. So it's therefore in conformance to ours. But there are places and steel mills that have better reputations than others. And I'm not going to get into the particulars on that, but I think it's a good idea to qualify the steel with inspection if you have any reason to be concerned.
Okay. Can you please clarify the ifs and buts associated with welding to A7?
I'll start out and try to clarify that. The welding to old steel groups in the AISC committee researched the historical editions of AWS D1.1. Back in the 1960s, it was actually called AWS D1.0. And when the historical AWS D1.0 admitted A7 steel into the standard for welding, it was very restrictive, just as we noted here. The thickness of any element in that cross-section should not exceed 1.5 inches. And again, that is probably a backdoor way of getting a piece of sound steel that has been manufactured properly. If you get thicker than that, the manufacturing process, it was probably something like an old-fashioned method that promotes unsound features, actually. In the age cutoff of 1950, the group is debating moving that up till 1960, given what we're seeing actually in 1950s and 1960s structural steel and how occasionally unsoundness concerns crop up. But if what you have is an A7 steel, no matter what its age, you should as a minimum do the microscopy metallography examination Robert mentioned. If you have to choose between compositional analysis and microscopy, go with microscopy first, because if it's an unsound piece of steel, that's almost certainly a deal breaker for welding. Otherwise, ideally, you would do all three, develop a sampling program for any piece or any building with A7, do the compositional and metallography analyses, maybe even the tensile testing if you're not sure of which vintage of A7 you are, because the specified minimum yield strength varied over the decades. And then when you actually go to weld and develop the WPS, you'll most likely be increasing preheat. If there is a multi-pass weld, then you'll definitely want to watch interpass temperatures and bump those up a little bit from what is typically shown in a pre-qualified WPS. Robert, did you have any further advice on welding to our older A7 steels?
Well, I would say you really have, in my experience, you probably have nothing to worry about other than soundness. The composition of A7 is very weldable. It may not have been intended to be welded, but steel mills didn't add carbon and alloy content to steels just for fun. They had, whatever they would add was for strength. If the steel, if it's A7, that's not really, that's sort of at the low end of the strength scale. So they weren't really doing anything to make the steel less weldable from a hydrogen cracking standpoint. So really the internal soundness is the only thing you have to be concerned with. And I think Conrad has covered that pretty well.
Okay, we've got time for one more question. If construction documents state that you're working with A36 steel and it's pre-1960, how likely is it that the steel could be dirty?
Robert, you take a crack first, and then I have a comment to introduce here. The ASTM A36 standard was not issued until 1960. And so if it's A36 and the drawings are pre-1960, that would be peculiar. It could be 1959 and they were anticipating ASTM A36, but it was issued as, frankly, tentative specifications starting in 1960 and running through about 1965 or 66 before it was made a non-tentative real standard. And Robert, you can comment on the weldability.
I would say from an internal standpoint, an internal soundness point of view, if it's post-World War II, you're taking about a 10% risk. If it's pre-World War II, you're taking about a 20 or 30% risk.
Yeah, and specifically the ASTM A36 standard was meant to be weldable from the get-go.
All right, that's all the time that we have for questions today. Like I said, if we weren't able to get to your question, at least one of the presenters will follow up with you to respond directly. Thank you, Conrad. Thank you, Chris. Thank you, Robert. That was a great presentation, and we really appreciate everybody taking the time to join us today. We hope it's been educational. Thank you so much for your time, and we hope you have a great rest of the day.